So we were talking yesterday about effective field theories and unitarity violation. So let me remind you of the effective field theory formalism. Right? Okay. So the effective field theory is an infinite tower of operators of higher dimension, where I just start with the dimension 6. And there are a lot of assumptions that go into this. Anybody know any assumptions here? Okay, symmetry. SU3 cross SU2 cross U1. And the rule is you got to write down all the terms that are allowed by the symmetry, okay? But there are more. Anybody else? Standard model fields, that's the really important one. Yeah, standard model fields. Let me write no light stuff. So if there were some light stuff around, this wouldn't apply. So it's the really depressing assumption that all you got is a standard model field. So you don't see anything else. Okay. And you assume it's weakly interacting below lambda. It scales less than lambda. Okay, so at low energy, this is a nice, well-behaved theory. So there are different ways to add these operators. The way we're going to do it is assume that the Higgs is a doublet. So you only add things like phi dagger phi, or other terms which are invariant under SU2. Okay? So one way to get started on this is to take the standard model Lagrangian and just put phi dagger phi in front of all the terms. So you'll get the first sort of collection of terms. Okay? So just for curiosity, it's been mentioned several times that the dimension 5 operators violate lepton number. Is that obvious to everybody, or should I show you why? It's obvious? No, it's not obvious. You're asleep. Okay. All right. Left-handed doublet in the standard model, right? The Higgs field, phi, what did I call it, C. This is the I sigma 2 times phi star. This is phi naught minus phi minus. Okay? That's just the conjugate of the SU2 field. So what do you notice about the Higgs field and the lepton doublets? They're identical, right? They got the same SU2 charges, the same electromagnetic charges. They're the same, right? So that means I can write terms, and I'm going to get all my factors right here just to be careful. 1 over lambda, psi bar left up here, I phi, let's erase this, phi j, epsilon ij, psi bar left, what do I call it here, k, phi left, epsilon k l plus Hermitian conjugate. So this is a perfectly allowed SU2 invariant operator, right? Because these guys have the same quantum numbers. So if I have psi bar left, it's like nu bar. So it gives a Majorana mass to the neutrinos, and it violates lepton number. So typically, when people who do electroweak physics are constructing their effective Lagrangians, they just forget about lepton number violation. Oh, these terms are very interesting for people who are constructing neutrino masses or doing neutrino physics. Okay. So I got this effective Lagrangian. What am I going to do with it? Well, I'm going to write down just one operator and sort of show you how the game is played. Okay, so a really simple operator is something called CWW, lambda squared, OWW, where OWW equals d mu w nu minus d nu w mu squared. Let me write it in the SU2. I plus I G W. What do I want to do? No, I'll do it the abelian case, sorry. I'll just do it like that. D mu squared. Okay, that's the abelian version. And then the non-abelian version, you're going to have the extra terms here. So this operator generates a number of terms, right? The first set of terms it generates are just 2-point functions. So these operators all contribute. Here's W. Here's my new operator. Here's a W with my new operator. Here's a Z or a gamma, Z gamma, and here's a W. So this contributes to the W mass, MW. And in general, all these new operators contribute to precision electroweak physics, right? You mess up the W couplings. So what do you think? Is this renormalizable? I got these operators which grow with S over lambda squared. You start calculating loops. Does it make sense? Is it a renormalizable theory? Anybody? You don't know. No? Yes? You say, of course not? No? Anybody else? Anybody for the sort of maybe? Depends on what you mean by renormalizable? Yeah. Okay. Sort of maybe. It depends on what you mean by renormalizable. Yeah. Okay. So what do I mean by this? Well, this was actually something that Weinberg did way back when he was writing down effective field theories for pions, which are just like effective field theories for W's, actually. Okay. So you calculate this thing with this new operator, and what are you going to get? You're going to get CWW over epsilon. You're going to get a bunch of poles, right? I mean, it's not finite, as you correctly noted. But what are you going to do with those poles? No, that you're not allowed to do that. But it's almost the same. So what you do is you can redefine dimension 8 operators to absorb the poles. Okay? So you get a bunch of poles at dimension 6 when you start calculating. And all you do is you redefine your dimension 8 operators to absorb those poles. And then you get more poles when you calculate with the dimension 8, and then you redefine them into the next order. So this is a theory that's got an infinite number of counterterms. So that's what I meant by maybe. Sort of, kind of maybe. Okay. So that's what you do with your poles. You just redefine the next order. And so on and so forth. Infinite number. Okay, so precision measurements from this, from the 2-point functions. You get MW and so forth. Okay, you're also going to get, as I talked, well, actually it's the same diagram. You get 3-point functions. Okay, so last night we had this nice talk about looking for unitarity violation in gauge boson scattering, and she was looking for quartic interactions. So why don't we look for the 3 gauge boson interactions? And there's a very good answer. Yeah, but you know the answer because you're working on it. Yes, that's exactly the right answer. Right. And why are they constrained? Where are they constrained? Okay, they're very, very constrained, and they're constrained from E plus, E minus, goes to Z gamma, goes to W plus, W minus. So here we go. So these couplings, we don't have to measure at the LHC because LEP2, which ran just slightly above the W pair mass, constrained all those operators excruciatingly well. And E plus E minus colliders, as Maxime, I think, pointed out, can actually constrain this stuff way better in the LHC because you know the incoming momentum here. So you know extra piece of information. You don't have to integrate with PDFs. So these guys are known from LEP. Okay, so that leaves from this, okay, so this is CWW. So that leaves the 4-point couplings to measure at the LHC. Okay, so one more point about these effective operators here, and using this effective field theory. Suppose I'm calculating my favorite process here, h to w plus w minus. We all know how to calculate that. So here we go. Here's h, w plus, w minus, and then there'll be some contribution from my new physics operator here. W minus from some CI. Okay? So I calculate this thing, and I get the amplitude for h goes to w plus w minus equals the amplitude standard model plus CI times the amplitude, what shall I call it? EFT. All right. So then I square this thing, CI over lambda squared. I square this thing to get the decay rate. Gamma h goes to w equals gamma standard model plus CI over lambda CI over lambda squared times something new from the interference plus CI over lambda squared from this term squared. Fine, but what's the problem with this? There's a logical fallacy when I do this. Okay? I calculated my amplitude and I squared it. But the logical fallacy with doing this, okay, so here's the lambda squared. Here's the 1 over lambda to the 4th piece from squaring it. But that's exactly the same size as the C prime over lambda to the 4th dimension 8 operators, right? So when I'm trying to look for new physics, this term, which I've decided to include, is the same size as this term, which I've decided not to include. Yeah, you're starting to see why this stuff is kind of messy, right? Yeah, so you can't do that, right? That's inconsistent. So what you have to do when you're playing this game is you have to find a regime of physics where this term is much, much bigger than this term. Yeah? If you're looking for parameters where this term is as big as this term, well, then you're not consistent. Right? So these theories have regimes of validity. You can't just use them blindly. Okay? Is that clear? Are there any questions? Yeah?
Where did the Z come from?
Where did the what come from?
The Z. So
what Z?
So you wrote that effective operator with O sub WW.
Yeah?
And you wrote the loop with the coupling to the Z. I think I missed something that it said.
Oh, yeah, because I wasn't being careful. I'm going to write that in terms of the SU2 gauge fields, and then after I diagonalize them, there's W1, W2, and W3, and W3 gives a contribution to the Z. I just didn't feel like working it out. But yeah, so you write it in terms of SU2 gauge invariant operators, okay, which then generate the Z in the photon. Yeah. Sorry, yeah?
I'm confused, but so if the new physics contribution is bigger than the standard model, then the
well, it better not be, right? Yeah, that's a good keep going.
but I mean, for some processes, the standard model is almost invisible.
Mm-hmm. So then it would be anomalously big, you say.
Yeah, and then the it'll be the other way around, right?
No.
Cortex,
No, you always have to have this expansion being valid. So when I take these operators and calculate, scattering processes, what comes upstairs? That dimension, that OI dimension 6 operator has dimensions, right?
Sure.
So when I calculate, so this thing has OI has dimensions of the mass squared, or energy. So when I calculate with that, I'm going to get corrections which go like m squared over lambda squared, or s over lambda squared, terms like that. The s will be if I have derivatives in my operator. So this whole expansion only makes sense if this is less than 1. Because if this, well, let me put the C here too. If this thing is not less than 1, then the next term is bigger and the next term is bigger, and it's a non-convergent expansion. So by construction, it's only valid when these terms are less than 1. Yeah. Yes? So if you have strongly interacting physics, which perhaps is what you're thinking of, you have to cut it off at an energy scale such that your expansion makes sense. Because you can't expand at something bigger than 1. You're still unhappy.
Yeah, okay.
You can ask the question in a different way maybe later, when you figure out why you think I'm swindling you. I mean, this whole thing is kind of an odd construction, right? It's saying, well, we didn't see anything new light, so we know that everything new is heavy, and we'll just assume there's nothing hidden there and assume that we can expand this way. So that kind of goes into where I'm starting. Okay. All right. So I've talked a lot about the rho parameter and calculating loops and so forth. So let's go back and review what that tells us about Higgs physics in the Standard Model. So what I'm going to say now is actually relevant for things like this. Okay. So let's forget about QCD for the next 15 minutes. We just have the electroweak theory. So we've got G and G prime as our coupling constants. And we've got mu and lambda from the Higgs potential. Okay. And as I said before, we're going to trade these guys for, let's see, alpha, G Fermi, MZ, MZ, and MH. Okay? Using relationships of the Standard Model. And the reason I'm going to do this is because these guys are very well measured. Except for MH, I suppose. So G Fermi over the square root of 2 is equal to G squared over 8 W squared equal pi alpha over 2, 1 minus MW squared over MZ squared times MW squared. Okay, I derived that in the first day. Okay, this is the tree level result, but I can invert it to get myself a prediction for the W mass. So I'm going to predict MW equals 80.939 GeV. So there's my prediction. All right, so Maxime showed you how they measured the W mass at the Tevatron, and he pointed out that the Tevatron measurement of the W mass is still the world's best measurement. Anybody remember what it is? Okay. 385 looks pretty good so far. It's pretty close, right? But the error on the W mass is plus or minus 0.015 GeV. Okay, so it's actually pretty far off this prediction here. Okay? So I can renormalize everything and find the corrections to this. It's just the usual way. G Fermi goes to G Fermi unrenormalized times, say, 1 plus delta G Fermi over G Fermi, and so forth and so on. Okay? So I'll put zeros on everything over here. 0, 0, 0, 0, 0, the unrenormalized quantities, and I'll just renormalize them all. However, when I look at this, I see that everything here is physical. G Fermi is measured in muon decay. Alpha is measured in Thomson scattering. MW is measured, it's physical. MZ is measured, MW is measured. Okay? Everything is physical. So it's a perfectly renormalizable theory. So what I'll do is now I'll take my zeros off. And zero's gone. Oops. And This isn't high enough. Let's see here. So, G Fermi, so now this is the renormalized guy, equals pi alpha over square root of 2 mw squared, 1 minus mw squared over mz squared. And I'll just lump all my radiative corrections as in 1 minus delta r. All these corrections I'm going to calculate to the renormalization of alpha, G Fermi, and so forth, I'll just put them in 1 minus r. Okay, well, something really interesting happens when you calculate these things. And I think Fred Jagerlainer was the first person to actually work out all these gory details, because it gets pretty messy when you actually do this. But let me just show you a few of the contributions. So delta R from the top quark loop, I'll put in the, it's a minus sign. That minus sign is important. 3/8 G Fermi over the square root of 2 mt squared over pi cosine theta w over sine squared. Okay, this is just cosine theta w is just mw over mz. Okay, so the contribution to these radiative corrections from the top mt squared, yeah, get the units right, it's a squared. Okay, so it's G Fermi mt squared, or mt squared over v squared if you like. So there are very, very large radiative corrections from the top quark which go like mt squared. And if you work out the sign here, it is such as to pull the prediction down closer to the observed value. So the prediction gets much closer to the observed value. Well, that's good, but what about the Higgs? Okay, the Higgs also contributes to this renormalization. Let's see, I'll put it right. Delta R from the Higgs, it goes like, I'm not going to write the factors. They're not that interesting. G Fermi mw squared, okay, times the logarithm of m Higgs squared over mw squared. Okay, so this is a general feature when I calculate corrections from the Higgs boson. I get things which are logarithmic and not quadratic, okay? So the dependence on the Higgs is always much weaker than the dependence on other physics. So I add a bunch of new Higgses or something. It's always logarithmic like this. Okay? Any questions here? So I just wrote these two terms. But there are lots of other contributions here. There are contributions from W's and Z's and photons. And in fact, the contribution from the Higgs has a 1 over epsilon here, which is associated with this logarithm. So that 1 over epsilon is canceled by all the W's and Z loops. So you can't actually cheat and just do contributions to things from the Higgs. You got to do the full electroweak thing if you're going to actually get something sensible. So this is just to demonstrate that it's logarithmic. Okay. So now we can do some really nifty things here. Okay. All right. So let me try to sketch a chi-squared plot here, which probably won't come out too well. So here's MW. Here's the delta chi-squared. Here's the measured value over here. Okay. So the first thing people do is they do a global fit to all the data that we have except for MW. Okay, so all of the precision measurements at LEP, you know, precision couplings of the electron to the Z, all the data we have, they do a global fit here. And you get a chi-squared fit that looks kind of like this. Okay, so it doesn't look too bad when you do this global fit, except the minimum here is over at, I erased the measured value. That wasn't too good. Okay, but it's off. It's more than the minimum of the chi-squared is actually more than 1 sigma off from the measured value. So it's not perfect. Okay, so this is no W in fit. So now let's do exactly the same fit, but add in the measured Higgs, remembering that it's a logarithmic dependence on the Higgs. And what you get is the minimum is still in the same place, but it's very narrow. Okay? And it's off from this. Okay. So things are good but not perfect is sort of the bottom line I want to add. Okay, so this is add in Higgs.
Sorry, what do you mean by no W?
Oh, you do no MW measurement. So you pull out the measured value. Thank you, that's a good question. You pull out the measured value of MW when you're doing a chi-squared fit. So what are you doing? You're saying all this data I have from the electroweak theory, which I told you from this can predict the W mass, I'll compare that with the measured value. So you're comparing two things to see if the theory makes sense. Okay, and this kind of analysis is now done at several loops. Okay, so the W mass is a little bit too high.
So the original bands were from
LEP and LEP2.
that's just the Higgs measurements from.
This is exactly the same, except I added in the fact that I know MH equals 125. Okay? So, let me just write here, G-fitter. There's a collaboration that's been around for a long time. At LEP, they called it Z-fitter. And this collaboration specializes in taking all the data of electroweak quantities, all the precisely measured stuff, and fitting it to the theory. So this is a really nice experimental theoretical collaboration. And they have a very beautiful web page that's worth looking at to look at these plots, for example. Okay? So you can, of course, play this game many different ways. The theory calculations are now pretty much all at 2-loop in the electroweak level. So they're very well advanced. But let's play this game a different way. Here's my favorite way to play the game. I'm going to put the M top down here and MW up here. Okay. Because I know that all these precision calculations depend quadratically on the top quark mass. Okay, now I'm going to put, we know the top quark mass is 173. So here's the experimental measurement. If you guys were making fun of my circles yesterday, you can really get going when I draw this plot. This one's not going to be pretty. But okay, so there we go. Here's the experimental measurement of the W mass, 80.35. Okay, here we go. So there they are. So now I'm going to take all my data from LEP and LEP2. Not me. G-fitter is going to take all their data from LEP and LEP2. Okay, so all precision data. To all electroweak. Okay, so all the stuff that depends on the W mass and the electroweak couplings and W exchange, and I'll remove experimental MW and MT. So I'll fit to everything I know, but I won't fit to these measured values. Okay, so the fit comes out that MW is a little bit high, and the fit sort of looks like this. Okay, so here's the fit. Hey man, that looks pretty good, wouldn't you say? Yeah, it goes right through the measured W mass, the top quark mass, you know, everything looks pretty good here. Yeah? So LEP2 was a long time ago, right? It was before the LHC, before you guys, you know, went to high school. It was a long time ago. So people have been doing these fits, you know, for a long time. So they did these. Okay, so this guy has, all right. This is a modern fit. Let me erase the middle so I can draw something else. I could try playing with colored chalk. All right. I'm going to play with, okay. So that line I drew doesn't have the measurement of the Higgs either. So let's just add in the Higgs. Can you see the red? Okay, so if you add in the Higgs, you get sort of a smaller ellipse. So things get really good. They really look pretty. So there's the measured Higgs. Okay. But as I was saying, this game has been going on for a long time. The folks at LEP, they had all these numbers. They had most of these radiative corrections. And they said, well, gee, they all depend on the log of the Higgs. Maybe I can, predict the Higgs mass. Okay, so here's MH equals 125. So if you take, say, MH, I don't know, 600, okay? It's way down here. And actually, I didn't make my picture big enough because it's way off. Okay, yes?
Sorry, I just cannot see very well. Does this Higgs go to the square with MW and MW?
It's a little bit below. It's a little bit below. The measured W mass, like I showed, that's why I showed you that chi-squared picture, is that the measured W mass is a little bit higher than the fit. And sort of by 1 sigma. And this has been around for a long time, that problem. Yeah. So what happens when you add the Higgs is it doesn't actually make the W mass quite big enough. But it does make the ellipse smaller. Okay? Yeah, good point. Thank you. So before I knew the Higgs, I could fit with heavy Higgs and do the same thing, and it's way off from the measured values, way outside the predictions. So in some sense, after LEP came, we already knew that the Higgs was light. If we believe these precision measurements, we knew the Higgs was light. We knew it wasn't 400 GeV exactly because it fits like this. Okay. So what's the loophole in that logic? There are always loopholes. What's the loophole? Anybody? Yeah? Yeah, exactly. If you were this all comes from radiative corrections, right? From calculating loops. So maybe there's something else floating around these loops, and that would invalidate this. So the first thing you do when you got a new physics model, of course, is you start calculating exactly these precision electroweak corrections to see if it makes it worse or better. Okay. So, yes?
How do you understand the fact that it's at least 1 sigma between the prediction and the...
Well, 1 sigma is 1 sigma, right? You don't really get excited until things are 3 sigma or something. Yeah. Do I understand it? No.
Yeah, but still you can add something else and say, like, if you add some other...
Oh, absolutely. Yeah, you speak like... there are a great many theorists, including me, who've played that game. You say, oh, I want to add something that's just going to pull this up, right? And yes, you can do it. Right. Yes?
What Higgs mass would have been required to actually fit the Dawson perfectly?
Oh, that's a good question, because this is 125, and it goes this way.
So it would have been a bit lighter, right?
Well, it would have been lighter, except at LEP, there was a limit on the Higgs mass that it was heavier than 115. Okay, so Felix, do you know the answer to that? Okay, the question is, and it's a really good question. Okay, so 125, you're a little bit below the W mass. 600, you're way off. How light do you have to go before it goes right through the measured values? Yeah. Somehow I remember 94. Does that rings a bell? Something like 94. So there was a conflict, yeah. But what happened is because of this logarithm, it wasn't very sensitive to that mass. Yeah. Okay. So, all right.
Is it a generic feature of scalars that they always enter with a logarithm into this?
Yes, it is a generic feature. Yeah. No, it's because of the SU2 structure of the Higgs. It always enters with a logarithm. There's something that's called the screening theorem, which I'm not going to prove, which says that the pieces which aren't logarithms always arise at the next order. So if I calculate G Fermi squared, for example, I would have pieces which weren't a logarithm, but they're always 1 order behind. Yeah. The proof isn't that interesting, but you can prove it in general. Veltman did this and gave it a name. Okay, so. All right. So this is really important and nice for the model builders, but it's actually also quite a bit of work, right? Because, for example, if I'm calculating the corrections to G Fermi, which are from mu goes to nu, goes to W, E nu, there are things like, let's put a Z like that. That's not a very good picture, but yeah, okay. So they're box diagrams. There are lots of complicated diagrams when I do this. And it's quite a bit of work. And so you got a new model, you're thinking about it, you want to see if it's ruled out by precision electroweak. So you want to do something easy. Okay. So there's an easy way. And the easy way says that, well, when I look at the corrections here, these boxes, geez, they aren't very important. In fact, when I look at the corrections, they mostly come from corrections to the two-point function. You get most of your oomph in physics from the two-point function corrections. So that led to an approach where you calculate something called ST and U if you're in America, epsilon 1, epsilon 2, epsilon 3 if you're in Europe, and they're exactly the same thing. Okay, so what these functions are parameterizations of the two-point function to take into account new physics. And the idea, all right, the idea is that if I write a two-point function, say pi, let's VV prime for two gauge bosons of Q squared, I can just Taylor expand this in the Q squared. So I'll write it as pi VV prime of 0 at plus Q squared over lambda squared d pi VV dq squared plus da-da-da-da-da. Okay, I'll just Taylor expand it out. And then I'll say, well, I got some new physics. I think the new physics is probably heavy. Say it's, I don't know, T prime at a mass of 2 TeV. It's, what's your favorite thing? Squark at a mass of 700 GeV. It's something heavy. So the effects of the new physics coming into this two-point function are going to be suppressed by 1 over lambda squared, or this term is going to be small. So I'll just keep the first term. I'll just keep the term at Q squared equals 0 here. So I Taylor expand, and I assume the higher order terms are small. Okay. All right. I'll leave my plot there. All right. So let me just write down the definitions. Alpha times T equals pi WW at 0 over MW squared minus pi ZZ at 0 over MZ squared. Alpha S is 4 SW squared CW squared over MZ squared pi ZZ at MZ squared minus pi ZZ at 0 minus pi gamma gamma at 0. Okay, so what do I mean when I say pi VV or so forth? If I calculate the two-point function of a vector boson mu nu, it's going to be G mu nu times pi VV plus Q mu Q nu times, what shall I call it, BVV. So this thing that I pull out is just the coefficient of the G mu nu term. Okay? So these are really easy to calculate for my new physics. All I got to do is calculate the 2-point functions for the W and the Z. I put my new top partner into the loop and I calculate these guys. Okay, so alpha t is just the W 2-point function at 0 minus the Z 2-point function at 0. Does that look familiar to anybody? Yeah, anybody? You know what it is. It's my favorite variable. Yeah, that's because you know it's my favorite variable, right? Equals rho. So this wasn't so deep and profound when people had that insight that, gee, the 2-point functions give me the rho parameter and they are an important limitation on new physics. Okay, the S parameter is essentially just the scaling of the Z 2-point from MZ to 0, right? Oops, this is MZ. Yeah, MZ squared. Okay. Sorry. So, and then I subtract off the scaling of the gamma gamma 2-point function from MZ to 0. So how come I don't have pi gamma gamma at 0 in analogy to pi ZZ? It vanishes by gauge invariance. The photon 2-point function at q squared goes to 0 vanishes. That's why it's not there. Okay, so this is great. I can calculate all this stuff. Yeah, it's easy. I can calculate it. So what do I get? I get the usual kind of stuff. I get alpha t from heavy fermions, say. It's going to go like the mass of the fermion squared times G Fermi. So that's nice. And alpha, I took out the alpha S. It's going to go like n color over 6 pi for a fermion doublet. And other values for other things. Okay. So the point is that T tends to be bigger than S, but S is still non-negligible. It gives you things like 1 over 2 pi. Well, this is pretty cool because it's dead easy to calculate. And you go back to my favorite web page, the GFitter web page. What's that? Good question. So the answer to that is the U parameter is a long formula that I didn't want to write down. It's well defined in terms of the 2-point functions. You can absolutely calculate it while you're at it when you're calculating your new physics. It tends to be smaller. In most of the models where I've calculated it, and in general, it's just numerically smaller. But yeah, you can calculate it and you can fit to it and so forth. But a lot of times people don't bother, just because it always comes out to be a little bit smaller. Never changes your fit. Okay. Yes, it does come in. That's a good question. And in fact, I will write it down, and then I will answer your question unless somebody else knows the answer. All right, minus CW squared minus SW squared over CW SW pi gamma Z of MZ squared. Okay, there we go. Yeah, it does come in, but typically it's 0. Fermions don't contribute to the gamma Z mixing. So if I have my new model with heavy fermions, that term doesn't contribute, which is why you usually forget it. But if I have some new model with gauge bosons floating around or something, it does contribute. Yeah. So, yes, thank you. Okay. All right. So what good is this? Okay, I go to my GFitter web page. And I see they've made a fit. They've made delta S, delta T. All right, this one is with U equals 0. They've actually made a fit to ST and U with the correlation matrix and everything else. So you can completely do it right. Okay, so here's... Okay, so why did I write delta S and delta T instead of just S and T? Well, when I calculate S or T here, I got a bunch of standard model stuff that contributes, right? The standard model particles contribute to all these two-point functions. The standard model Higgs with the standard model couplings, all this standard model stuff contributes. So what they fit to is actually delta, say S, equals S standard model, all the standard model stuff, minus S nu. So this is even cooler when you're doing your new physics model, right? You just got to calculate the S nu stuff. You subtract out the standard model stuff, say somebody else took care of that, and you just need your new stuff. This is great, guys. So it's the first thing you do with your new physics models. So you calculate delta S, you calculate delta T, and you fit the parameters so that it's in the experimental box. Yes?
If you did have new physics from, say, another SC2 group, when you have additional parameters, how are these parameters just enough if you have additional gauge bosons?
If you have initial gauge bosons?
Additional gauge bosons. Yeah, like additional things that look similar to W's and gamma.
Well, you know they're much heavier, right? So you just run them in the loops. Right? So it's this Taylor expansion approximation. People have actually kept the next terms in the Taylor expansion.
No, but I mean, wouldn't you have to have more parameters than just ST and U, or redefine the ST and U parameters because you would have things like...
Not if they're heavy. Not if they're heavy. Because the assumption behind all of this stuff is that everything new is heavy.
How heavy would you say? How heavy though?
How heavy? Well, the expansion parameter is actually mz squared over m new stuff squared. So your w primes, the expansion in mz squared over mw prime squared, that new scale, would have to be good. So if they were light, it wouldn't work. But if they're heavy, it does work. So there's a Taylor expansion. So there's nothing deep here. So there are people who added 6 more parameters, STU and then UVW. I forget what they call them. But they added the next terms in the Taylor expansion to do this. But once you start doing that, then you start thinking, well, why don't I just do the calculation right? I mean, the only advantage of this is that it's dead easy, right? You can get an idea for the allowed parameters. Yes?
Yeah, so basically you drop the derivatives of the...
Yes, that's the assumption. So that's the assumption that the new physics is heavy.
But I'm seeing some sort of derivative in S there.
Right, this is the first term that comes in S. Yes, so you keep the first term in your Taylor expansion. Okay? So in T, this is the first term. So the idea is that each of the derivatives is suppressed by 1 over lambda squared. So you keep the first term, yeah. Yes?
Right, so for example, so in the standard model, the contribution to T comes, say, for example, from the fermion sector, because the top you have and the bottom you have are different.
Yes, it's mt squared. Mm-hmm.
And it's very custodial symmetry.
Yes, absolutely.
So somehow I can think in the back of my mind that T is measuring this rate.
Yes.
But so you're saying that
S essentially counts the number of fermion doublets.
and this is irrespective of whether...
Yeah, see this? Right, this doesn't depend on the mass at leading order. Yeah, right. So you notice the wiggle there. Yes, the wiggle there.
But so I could add like a lot of fermion doublets, and as long as you have, are equal for the...
I add a whole bunch of heavy fermion doublets, say.
Then I don't contribute to T, but to S.
That's going to screw up S. And that's a really important point, because the people who did Technicolor, anybody know what Technicolor is? Except for Felix, because he's older than you guys. Anybody else? Okay, so Technicolor was a theory where you were going to break SU2 not with a Higgs, but with a condensate, with some heavy interactions, okay? Sort of like the pion in SU2. And in order to actually make the theory work, you needed a whole boatload of fermions. And essentially, it's this limit that kills those theories, well, among other things. But so it counts the number of fermion doublets. Yeah. So anybody else? Yes?
Yes, so you have this custodial symmetry to protect T, right?
Mm-hmm.
Is there a similar symmetry to protect S?
No.
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 Is that a proven fact?
Yeah, because it just counts doublets, essentially. I mean, this is the number of doublets, right? right? So you got one doublet, TB, it's 3 over 6 pi, it's 1 over 2 pi, and so forth and so on. Yeah.
So surely if I take the mass of my fermions to be very heavy, his contribution to it should go away, right?
No, because it's like the log of the ratio of the fermion masses. So as long as there's not a big splitting, it doesn't go away.
That seems weird because it should decouple, right? There should be something continuing.
What makes you think it decouples? I mean, fermions coupling. And it's, the standard model, I mean, fermions don't.
Like
Yeah.
if I just add a bunch of vector-like fermions, are they very heavy? Like,
They still contribute. I'll show you an example, actually, with vector-like fermions. I'm going to work it out.
okay.
Yeah. And you'll see why they don't, why it's not obvious that they completely go away. Any more questions on this? Okay. Okay. So I'm going to change. Why? I'm writing myself a note to write down the exact formula for S. Okay. So, all right. So now I'm going to go back in the rest of today and tomorrow. I'm going to talk about gluon fusion, my favorite process. And why is gluon fusion so interesting? Well, for one thing, it gives you limits on fermions, in particular like vector-like fermions, so it's important. But the gluon fusion process is often can be used to measure the width of the Higgs, and a very clever idea that uses the fact that Z's are longitudinal. So I'm going to work through gluon fusion. Yeah, it's really cool how you can use gluon fusion, goes to Higgs, goes to 2 Z's, and it has all this intrinsic physics of the standard model that half the physicists my age were saying, duh, why didn't I think of that? It's so, you were saying that, right? It's so completely obvious once you know the answer that I can't resist it. Okay, so I guess since I'm changing topic, I'll change the blackboard. All right. Okay. So I'm going to start with glue goes to H, and then either at the end today or tomorrow I'll have the H goes to 2 Z's, or I'll have glue goes to 2 Higgses. So it's all glue goes to H. All right. And it comes from my favorite diagram, where this is a Higgs and this is a top quark. Okay. So in my notes, I worked this out with all the minus signs and i's and the Feynman parameterization and everything else. It may be useful to some of you. I'm going to sketch where the physics comes. You've all talked about decoupling this morning, right? Bogdan's talked about decoupling. We all talk about decoupling. And this is the perfect example to actually see how decoupling works in the Higgs sector. Okay, so the partonic cross-section, GG, goes to H. It's equal to 16 pi squared over MH, 2J plus 1 times 1 over 64 times 1 over quarter times 2 gamma H goes to GG times delta of S minus MH squared. Okay, Maxime wrote this formula down for QQ bar goes to MZ, right? It's exactly the same formula as Maxime had. J is equal to the spin. So for the Z, it's 1, and for the Higgs, it's 0. The 1 over 64 is the color average. You got 8 gluons. The 1/4 is the spin average. Anybody want to tell me what the 2 is? There's physics in that, too. What's that? Yeah. Hey, that's good. When I calculate the decay H goes to GG, they're identical particles, so there's a half in the final state. I got to take that half out when I'm calculating the cross-section. Okay, so there we go. So I'm going to just sketch how this goes. Let's see. So this will be P mu, and this will be Q nu. And there's also a diagram where the gluons are crossed, of course, which gives exactly the same answer. Okay. So the amplitude for this guy is going to go like m over v from right here. Integral dnk over 2 pi to the nth times some numerator times some denominator. So far, so good, right? Okay, so the physics here is this numerator, T mu nu, is equal to, let me just write it down, trace K plus M, gamma mu, K plus P plus M, K minus Q plus M, gamma nu. Okay. So you notice something funny about this. Okay? How many gamma matrices are there in here? Come on, guys. You're taking the trace 1, 2, 3, 4, 5. What's the trace of an odd number of gamma matrices? 0, right. Yeah. So what's that tell you?
Proportional to the top.
Yeah, that tells you that this has got to be m times something or other. So only the terms with 4 guys come out, right? Yeah? Yeah. Okay. Oh, you're looking at my notes, huh? So you know the answer. Good. So if I made a mistake, you can tell me. D. So the denominator is k squared minus m squared. Let me just write it down after the Feynman parameterization. mh squared xy cubed. So there are 3 propagators downstairs. So it goes like 1 over k to the 6 here, okay? So we can all do this integral. I was asked why you do it in dimensional regularization instead of in 4 dimensions, because it turns out it's finite in the end. And in fact, Felix will remember this, there was a paper right before the Higgs was discovered saying that all the calculations that people had done of this, actually they were talking about h to gamma gamma, but it was the same thing, they were all wrong. And they did it in 4 dimensions. And what happens when you do this is you pick up pieces here from k squared terms, which give you poles, which cancel other poles. And so there's this delicate cancellation here that you have to be very careful with. If you just blindly go ahead and calculate in 4 dimensions, you actually get the wrong answer. You have to actually think about it. Okay, so here we go. So the amplitude is m over v. And we pull out an extra m for the trace. Okay. All right. So the amplitude, alpha s, there's a mistake in those notes. It's only 1 power alpha s. Unless these notes are wrong. It's alpha s m squared over pi v delta AB, the gluon colors are the same, g mu nu mh squared over 2 minus p nu q mu integral dx dy, where these are Feynman parameters, 0, 1 minus x, 0 to 1, 1 minus 4x xy over m squared times 1 minus mh squared over m squared xy, epsilon mu of p, epsilon nu of q. Okay, so this is just doing that diagram. So what do I learn from this? First of all, this form here, g mu nu mh squared over 2 minus p nu q mu, that's the form required by gauge invariance, because we know that, say, P mu dotted into the amplitude and Q nu dotted into the amplitude has to be 0. So this form is required by gauge invariance. So this is the form for a spin 0 amplitude. So if I'd gotten any other tensor structure, it would have been wrong. I knew I had to have that form. But the other thing is that I've got these two m squareds here, right? And I've got the 1 over m squared there. So I'll just erase the m squareds. Okay. So the amplitude is alpha s over pi v times this integral here, okay, which you guys can all do on Mathematica, right? Or you could just do it in the limit mh squared over mh squared over m squared, much, much less than 1. It goes to a third. Okay, so the amplitude is alpha s over 3 pi v times some stuff. Doesn't depend on the fermion mass at all. So this is decoupling. This is how you show decoupling in this case. Okay? So it wouldn't work if this coupling weren't proportional to m, right? So, and this argument holds for anything that gets its mass from the Higgs. So anything that gets its mass from the Higgs, it doesn't have to get all of its mass from the Higgs. You're going to have this kind of argument. So it doesn't depend at all on the Higgs mass in the limit that the Higgs, or on the fermion mass, in the limit that the fermion mass is heavy. So cool. So what does that mean? Okay. Well, let me just square this thing. Sigma GG goes to H is alpha s squared over 576 pi v squared delta of 1 minus s over mh squared. There you go. That's the large mass limit. Oh. And exactly the way Maxime told you to integrate the QQ bar goes to Z with the PDFs, it's exactly the same thing here, except you're integrating with the Gluon PDFs. Okay, so suppose I had a fourth generation. So I had a fourth generation, let's call it TB left, T right, B right. With SU2 cross SU3 cross U1 quantum numbers exactly the same as the standard model. So then these guys would contribute to top quark or to Higgs production, right? So I would have T and they would just contribute in exactly the same way. All right, so let's go over here. I know those guys are heavy because we haven't seen any heavy fermions. So I would have a top quark contribution to Glu goes to H. I would have my new top quark contribution there from T. And I would have my new B quark contribution because this guy is heavy, squared. So the Higgs cross-section would be 9 times the standard model value. So you don't have to think very hard about limits or radiative corrections or anything else. You know the Higgs cross-section can't be 9 times the standard model value. Okay? So first consequence, we can't have a chiral fourth generation. It's completely ruled out by the fact that chiral fermions don't decouple. There you go. Okay? Is that clear? Yeah. Yeah? Okay, so we still want to add new fermions. Lots of people are talking about vector fermions. We heard a talk last night about vector fermions, right? Okay, so why are we still talking about vector fermions? Well, turns out that they're actually kind of different. So the simplest kind of vector fermion I could add would be a top partner. And by vector fermion, what you mean is always that the left and the right-handed particles have exactly the same transformation under all the quantum groups. So T left, T right will make them SU2 cross U1 singlets. Okay? So this is sort of the simplest way I could do this. So what kind of interactions can I have? Let me go back to my potential. I got the standard model. So that'll have some Yukawa coupling. Q bar left, phi C, T right. So here's my standard model. So if I add a heavy top quark that's a singlet under SU2, it can have a coupling just like this. What do I call it? Plus lambda 2 Q bar left, phi C, big T right. I can couple lambda 3 T bar left, T right, because these guys are both SU2 cross U1 singlets. And finally, I can have a Dirac mass, lambda 4 T bar left, T right. Okay, so the Dirac mass of these vector-like quarks has nothing whatsoever to do with electroweak symmetry breaking. Okay, this guy you can actually rotate away. And you can rotate it away by redefining big T right. Oops, I'm too low, sorry. You should have stopped me. Okay, so you can redefine big T right here to rotate this term away. Yeah? What? I can't hear you. Oh, no, I mean, yeah. I mean that, yes, thank you. What I mean is that these guys have same quantum numbers as T right. And how did Felix know that I was being sloppy? Anybody? Well, he knew I was being sloppy here because the electromagnetic charge is essentially T3 plus Y. So these guys are going to be SU2 singlets, so the hypercharge has to give you the electromagnetic charge. And that's how he knew that I was being sloppy. Thank you. Yes. Okay. So this is the simplest extension with fermions you can possibly have. Okay? It's got two heavy top quarks, left and right, charged 2/3. They're allowed to mix with a standard model doublet, and they're allowed to have a Dirac mass. Okay. So there's a mixing here for the gauge eigenstates, because you put phi, take the V piece here, or for the mass eigenstates. So when I find the mass eigenstates, they're going to be mixtures of the standard model top and this new vector-like top. Okay, so the physical particles have some component of each of the things I started with. So we'll have T1 equals the cosine of some angle alpha times T right, right, plus sine alpha right times big T right. And T2 right is going to equal minus sine alpha right, T right, plus cosine alpha right. Okay, where these are my physical mass eigenstates. Okay, so here's the top quark and here's the heavier guy, and you guys can all diagonalize 2 by 2 matrices. Yes, you can do it. I know you can do it. Okay, So after you diagonalize your 2 by 2 matrices to find the mass eigenstates, you can go back and find the couplings of the mass eigenstates to the Higgs, right? You just diagonalize it. It's fun. Okay. So let me just tell you the answer. So here's the Higgs couplings, and here's, we'll say T2 is the heavier guy. Doesn't matter. So this guy is going to be cosine squared of alpha, and this guy is going to be sine squared of alpha.
It's a D1. So.
Yeah. There is a T1, T2 coupling, which is proportional to sine alpha, cosine alpha, but that doesn't enter into Higgs production. Sine squared alpha. But it does enter into double Higgs production, which makes double Higgs production super interesting for this stuff because you get mixtures of T1 and T2 transitions. But that's for the future. Okay, so what's that mean? Okay, I did this. Why is this like interesting and cool? Yeah. That's why it's cool. All right, so I've got my favorite process, glue. Here's my T1 Higgs. Here's my T2 Higgs. And gosh, I get the amplitude is going to go like the standard model piece times cosine squared alpha plus sine squared alpha plus order 1 over m T2 squared, right? Because this assumes I was taking the heavy top mass limit of those amplitudes. So you get the standard model rate out plus some small stuff. Man, this is cool. This says that if I add this particular version of a vector-like quark, I essentially get the standard model Higgs rate. Okay. And in fact, it's even more general than that. Because what am I doing here? I'm diagonalizing my mass matrix with unitary matrices. Yes? So when I work out the unitary matrices, they come in here and you get like products of unitary matrices like V dagger V. You still get one. So in these models with vector-like quarks, I can add as many as I want and I don't get big effects in the Higgs sector. Is that clear? Because it's kind of cool. So you can't add a chiral fourth generation, but you can add heavy vector-like quarks. Okay? So that's nifty.
Does this mean that you could add any vector-like quark as a partner to the standard model fermion?
Well, the standard model fermions, you kind of know what they are, right? So you can add, people try to add things which have, let's call it TB left, TB doublets like that, where you have a copy of the standard model, okay? This tends to run into problems because, so the top quark gets these changes in its couplings, right? Okay, but if I have a doublet, the B couplings are also changed. In particular, the vector-like B couplings to the Z are changed. And as Yuval was emphasizing, those are really well measured. You're not allowed to mess around very much with the couplings of the charge minus the third guys to the B's. So you can kind of stand on your head and do this, but it's very unattractive. What's more fun that people like to do is they'll add stuff xt, where x is charge 5/3. We heard about this last night. That's kind of cool. Or they'll add stuff like where this guy is charged minus 4/3. So they'll try to add vector-like multiplets with funny charged particles. That's what we heard about. Yeah? So, okay. All right. Okay, one more thing to answer your question about what happens to the S and T parameters in these models. What happens is that these things, these mixing angles are actually determined in terms of the parameters in the Yukawa that are the parameters in the potential that I started with, okay? So I can figure out what these guys are. And sine theta, well, the Yukawas, how do I, sine theta has got to go like lambda i's times mt squared over m big T squared. So in point of fact, these guys decouple as the mass of the top gets heavy unless the Yukawas become strongly interacting. So it decouples because all the parameters are connected together. So when I calculate, say, delta S or alpha. So when I calculate delta S or delta T, I get factors of this kind of hidden in there, right? Which says that decoupling requires, for fixed lambda, that you have this relationship. Okay, so, all right. Okay, I have time to do just a couple more things. All right. Okay. So let's go back to my favorite topic, effective field theories. We got this amplitude for GG goes to H, which was alpha S over 3 pi V. Was it mh squared? I think it was mh squared over 2 g mu nu minus p nu q mu. Okay. So we got this amplitude, but now I want to show you that you can derive that amplitude from an effective interaction. So suppose you had an abelian term, just because I'm lazy here, g mu nu in your Lagrangian. What's that going to give you? Okay, so this is d mu, well, let me call it A so we don't get confused. A nu minus d nu A mu, d mu A nu minus d nu A mu. Okay, so I can take the derivatives. D mu goes to I k mu when I'm finding my Feynman rules from here. And this guy goes to minus, I want to get my signs right here, k1 mu a1 nu minus k1 nu a1 mu, k2 mu a2 nu minus k2 nu a2 mu. Okay, so you can play around with your algebra here, and you can show that this g mu nu, g mu nu just goes to 2 k1 dot k2 g mu nu minus k1 nu k2 mu over k1 dot k2. Huh, that looks kind of familiar, right, with what we got from the gluons? Same kind of tensor structure. So if I defined an effective Lagrangian H G G minus alpha S, let's see, alpha S over 12 pi V G mu nu H, I actually get back exactly what I started with. Okay. So when you work out the details, if you work them out, you're going to say I screwed up a factor of 2. Where do you think that factor of 2 might come from?
Equal states?
What's that?
Equal states?
Nope. It comes from me being lazy because these guys are really have color, right? And when I did this guy, I had a trace TA TB equals delta AB times a half. So it comes from the color factor that I didn't put in over there. And actually all the factors, all the minus signs work out. So we can see that the large top mass limit comes from an effective Lagrangian, which is g mu nu times h. So in the standard model, I get this effective Lagrangian. And this effective Lagrangian is extremely useful. I mentioned that people calculated radiative corrections to the Higgs and the large M top limit. They do it using this effective Lagrangian, where I have tree level vertex for the lowest order process. So, okay. Well, I could either stop now or go 5 minutes late. And since you have Bogdan and a long day, I'm going to stop now, because I think you're probably tired. Okay. So next time I'm going to work out the low energy theorems, and I'm going to work out measuring the Higgs mass with glue goes to Z. I'm going to talk about double Higgs production, and then I'll probably run out of time. Okay. Coffee time.